Today we will be learning about NLP using transformer models and how translation works. Here are a few questions to ponder over. What is deep learning for NLP? How machine translation works? How Google Translate drastically improved after the year 2017? And why transformers gave rise to BERT, GPT, XLNet, and so on. Deep learning for NLP. As discussed in the earlier lessons, we know that when the machine takes the documents as the input, it detects the language, that is English, Spanish, Arabic, and so on, tokenizes the language, that is, breaks down the language into its specific elements, uses parts of speech tagging to identify which part belongs to which part in the grammar. For example, a particular word may be a noun, verb, and so on. Then we had the removal of stop words, which removed the unnecessary words which were redundant and which could reduce the size of the sentences. Then we have the feature extraction, modeling, inference, and the output. Neural machine translation. Major improvement of this was done from the earlier SMT standards. The transformer model introduced in 2017 revolutionized and became SOTA. The transformer models used were BERT, GPT, and XLNet. Neural history of natural language processing involved natural language models in 2001, multitask learning in 2008, words embedding in 2013, neural networks for NLP in 2013, sequence to sequence model in 2014, which we have discussed in the previous lesson, attention in 2015, memory based network in 2015, and pre trained language models in 2018. Five models are neural network, recurrent neural network, encoder decoder model, attention model, and transformer being the latest model. What are the applications of each of these models? The first model, neural network, can be used for word representation using the word to vec library. Recurrent neural networks can be used for language generation. An encoder decoder is used for translation. Attention models is used for translation and image recognition. Transformer model is used for translation. The first model we will be discussing is the neural networks. Neural networks are also known as artificial neural networks or simulated neural networks. These are a subset of machine learning and are at the heart of deep learning algorithms. Their name and structure are inspired by human brains, mimicking the way that biological neurons signal to one another. The neural network acts as a black box that takes an input and predicts an output. Here we can see that a particular number, a handwritten number, is categorized and then the machine reads it as the number one. Artificial neural networks are comprised of node layers containing an input layer, one more hidden layer, and the output layer. Each node or artificial neuron connects to another and has an associated weight and threshold. If the output of any individual node is above the specific threshold value, the node is activated, sending data to the next layer of the network. Otherwise, no data is passed along to the next layer of the network. In the previous model, we can see that the inputs being x0, x1, x2, and weights are given to the black box, which predicts an output into the cost function. Input is given to the layer. This layer we see here, layer 1 and the layer 2, comprise of the hidden layer. The input being the first layer, which is the input layer, and the output layer being third layer. The second layer is the layer 1 and layer 2, which consists of transforming the input using new weights. Notice how a cycle is formed here with the output, where output predictions and true targets combine to form the loss function, which is given as a backpropagation to the new weights, which in turn helps improve the hidden layer, that is layer 1, layer 2 outputs. The black box that takes the input and predicts an output. The box that takes in the input and predicts the output is known as the black box. It is trained using known input and known output. So in the previous diagram, we can see that there's a value called true target. This true target refers to the expected output. The true target and the predicted output combine to form the loss function. Together, the known input and output approximates the function and maps the new input. So as we see here, the expected value and the predicted value combine to form a loss function, which is given as a back propagation, which is fed as a new weight, which gives the model or function to the incoming inputs. So in uh, in a brief note, we can say that the earlier inputs, the later inputs are dependent on the earlier inputs. Using the word to vec in neural networks. Using the word to vec, we can see that the sentence, the quick brown fox jumps over the lazy dog, can be trained to give the quick and the brown as training samples. And when we use quick as the keyword, we have quick and the quick, brown and quick and fox. So here we are seeing that every keyword can be mapped with the other words in the list of considered words. And a similar pattern follows when brown becomes the keyword and fox becomes the keyword. This is a representation of how the input layer representation of how the input layer, you can name it as 1, the hidden layer where the function takes place 2, and the output layer being 3. The hidden layer, the layer 2, is where all the functions take place, and as seen in the previous diagrams, the output from this layer, the third layer, is given back as a feed to the hidden layer to perform functions on the incoming inputs. Word to vec using that neural networks, uh, we can address particular words to a particular category. For example, a king being referred to a male, a queen being referred to a woman, cat being categorized under the class of cats, dog being categorized under the list of dogs. Paris being a part of France, so London being the capital of England or part of England, he being a part of himself, and so on. Notice, however, that there is a portion here which seems a bit confusing because a father to a girl and a mother to a boy, how is it related, you may ask? Well, the words used before are singleton words, but the word mother is a relation. It gives a relation with respect to something else. So a mother can be with respect to a boy or a daughter. A father can be with respect to a son or a girl, and so on. In the next section, we have slow, slower, slowest. All of them, this can be categorized under the category of slow. Similarly, fast, faster, fastest, and other forms of the word fast can be categorized under the one head of fast, and so on. Word embedding captures the meaning of the word. How about sentences? Can we encode meaning of sentences? You can't cram the meaning of the entire sentence using the dollar, percentage, exclamation marks sentence into a exclamation mark dollar vector. Sentences are variable length. They need fixed length representation. In the second model, we have the recursive neural networks. A recursive neural network, or RNN, is a type of artificial neural network which uses sequential data or time series data. These deep learning algorithms are commonly used for ordinal or temporal problems such as language translation, natural language processing, speech recognition, and image captioning. They are incorporated into popular applications such as Siri, voice search, and Google Translate. Like feed-forward and convolutional neural networks, recurrent neural networks utilize training data to learn. They are distinguished by the memory as they take information from prior inputs to influence the current input and output. While traditional deep neural networks assume that inputs and outputs are independent of each other, the output of a recurrent neural network depends on the prior elements within the sequence. While future events would also be helpful in determining the output of a given sequence, unidirectional recurrent neural networks cannot account for these events in their prediction. RNNs are used when the inputs have some state information. Examples include time series and word sequences. These can capture the essence of the sequence in its hidden state. If you want to explore, you can go through this link given in this slide. RNN unrolled in time. So we have the function here with the input xt and the output ht, where a part of the output is given to the black box and which is reiterated back into the function. This can be elaborated as follows. When x naught is a, the vowel, or rather the article a, is given as input and it produces an output. A part of that gives the new weights to the function in next function, where the input is the word girl. The output from this is given as new weights to the function in the next scenario, where the input has walked, and so on until the value of until the last word or the last input, where the last input is x of t, t being the size of the sentence. In recurrent neural networks, we have the input layer, hidden layers, deep if greater than 1, and output layer. We have the different classes of recurrent neural networks, that is one to one, one to many, many to one, many to many, which can be of two different types. That is a fewer number of inputs and larger number of middle layers and the same number of outputs as the inputs. Notice how the number of inputs and the number of outputs is always to remain the same. Recurrent neural networks can learn sentence representation. So this is a graph of the different sentence representation. We have been discussing about how the previous inputs can determine the next input. Rather, the output of the previous inputs can determine the next input. When we have the history of the words, that is, in this case, you have can you please come. So when we have can you please come, the next word predicted can be here, there, and so on. But the most common occurrence after the history of the words can you please come is here. So that is the first word that has to be predicted. If the word here is wrong, if it's determined as it's wrong, then it goes to the next most popular or most common occurring word, that is there. But there does not make any sense. So it checks whether the sentence formation is correct and then proceeds. Recurrent neural networks can learn a probability function using previous words. This is an example of recurrent neural network training. Recurrent neural network can encode sentence meanings. It can predict the next word given a sequence of words. It can be trained to learn a language model. Problems faced by recurrent neural networks are that it is hard to parallelize efficiently, and backpropagation through variable length sequences is difficult. Transmitting information through the bottleneck, which is the final hidden state. Longer sentences lose context. For example, I was born in France to I speak fluent French. There are improvements to RNN structure that retain the context. The first attempt at translation was done by recurrent neural networks, in which it first creates the context and then uses the final context of the first RNN. Training by using the parallel corpora. The input is given to the encoder and which takes it to the decoder and then the output is formed.